Hey, student. Today I'm going to talk about basic electronics. Start from Series 1. It's just like Bible of electronics. We start from a very basic of electronics, and then we move to more complicated, and then hopefully student will understand more about what's going on in electronics. Well, we are start by talking about our components. The first one that something that we need to take a look in electronic circuit. In general, we are involved with voltage, with the unit of volt, current with the unit of ampere, and resistance in ohms. And later on, we will talk about our capacitor and inductor. Okay, let's start with the voltage and the current simple rules. Many students understand about KCL and KVL, or KCL is like Kirchhoff current law. When you are focused on any kind of node, um, when you consider current, you simply say something like the summation of the incoming current is going to be equal to the summation of outgoing current. As from the picture here, you're gonna see that I does mean is the incoming current equal to I1 plus I2, so they also are outgoing current, or it just simply is come from conservation of charge. The next one, actually this one, the KCL, you apply when you have like many nodes in your circuit, and you can analyze to find current at each point or across any devices, across any resistor. Either in devices, for example, like you have a resistor either in series or in parallel, you'll be able to calculate for any current that flowing through that kind of resistors. Next one is the Kirchhoff voltage law, or simply KVL for the short. You consider the loop on any circuit loop. You know that the source voltage V here is going to be the voltage drop across resistor, and the voltage drop across inductor. So you simply write down V equal to VR plus VL. We use like two conditions. Sometimes you have two unknowns, so in math you need two equations to be able to solve for those two unknowns, or if you have three unknowns, you need three equations. So this is going to help you to solve for the current or the voltage. The last one, you're talking about a power dissipation on any kind of devices, or here is resistor. P simply equal to I multiplied by V, and then you can play around with this one. You may write down P in the term of V and R, or even in the term of I and R. Okay, so this is the very simple concept. And you cannot miss Ohm's law, which states that V equal to IR. You take a look at the picture here, the current flowing from the left to the right, and then of course the current flowing from the lower voltage to the higher voltage. So you can write down from V equal to AR, V equal to AR, you can write down V2 minus V1 over R equal to I. So it seems to be very basic equation here, but when you get into complicated circuit, you keep in mind that you are have to play around with these three equations. That's mean Ohm's law, KVL, and KCL. Now let's take a look at resistor in series and parallel. In series, when you connect resistor in series, you can do all phi R total is going to be R1 plus R2 or plus R3 and so on, and then plus Rn. You can find the R total represent for the resistor system here. Now our resistor in parallel is simply write down 1 over R total equal to 1 over R1 plus 1 over R2 or plus 1 over R3 and so on, plus 1 over Rn if you have like n resistor in parallel. And from this R in parallel, if R1 equal to R2, R total simply is going to be half of 1 of resistor. For example, if you have R1 is 10k ohms and R2 is 10k ohms, your R total simply is going to be 5k ohms, so it becomes half of 10k ohms. In the circuit, if you connect R in series, you know that your current is going to flowing through R1 and R2 is going to be the same, but the voltage across R1 and R2 is going to be different. You can apply Ohm's law, V equal to AR, and then you can find the voltage drop across each R. For in parallel, it's going to be the opposite. You're going to have voltage drop, voltage across each R, R1 and R2 is going to be equal because they connect to the same point. But your I is going to be different depending on R1 and R2. But if R1 and R2 they are equal, you're gonna have the same current flowing through R1 and current flowing through R2. Now we're talking about power dissipation. You take a look at the simple circuit here. You have the source voltage and R in series with the source voltage. You can find the power drop across R to be V squared over R. For example, if I put V equal to 15 volt and R is equal or greater than 1k ohms, you can find the power dissipation to be 0.225, and actually I want to point out this one is less than 1 over 4 watt or 0.25 watt, which is resistor rating. You cannot exceed the power across R more than 0.25 watt, but it's usually become 2.25, so it's always less than 1 over 4 watt or the resistor rating. Now take a look at if you want to send the power through the wire, electric wire, you can calculate for the power loss. In this case, if you you have the source voltage to be 110 volt, so the power loss is going to be V squared over R, and then your R is 0.05 micro ohms per foot. So you divide V squared by 0.05, 10 to the negative 6, and that's give you 2.42, 10 to 11 watts, and that's exceed the power that you want to transfer your power to the end of the wire. So this one actually is turn out to be heat. The other one is often used, is we call voltage divider. The voltage divider, we use that just for to reduce the voltage. When you have the input voltage to be V in and you want V out to be less than V in, we have to connect, R in series, just like this one, and we take this one as the output here. This is we call voltage divider. That means you divide V in from the start, and then you multiply by R2, divide by R1 plus R2, because R1 and R2 are in series. Or you want to check it out, V out from the voltage divider, you can just like write down equation like this one. But if you want to prove, you can take a look. You want to find V out. Since R1 and R2 connected in series, you can find the current flowing through both R1 and R2. So it simply become from Ohm's law, I is going to be equal to V in over R1 plus R2. Now you want to find V out. This is your V out, or the voltage across R2. You simply multiply the current by R2. So VR2 equal to AR2, and your I just right here. So you substitute I, and then you multiply by R2. So it's going to be exactly the same equation, just like you derive from here. Now there's something interesting here. You can see that VR2 actually V out. In general, you can see that your V out is going to be less than V in always, except your R1 is become negative, because if this one become negative, it's gonna subtract from R2. So the ratio here is going to be greater than 1. So you have V out is greater than V in. It's become amplifier, and that can happen in some electronic devices, for example tunneling diode, and we will talk about it later on. And this one I show you, you can even be able to adjust your V out by connect or something that we call potentiometer or adjustable resistor. You can get your V out as you want. Next, we take a look at the voltage and current sources, and this is one of important that you have to consider when you are talking about a voltage source. You want to supply, the voltage source is just like a black box, and you want to connect electronic devices, and that's we call load, to the voltage source. The problem is that just for example here, when you have battery, 9-volt battery, and you have our internal resistance or the source resistance 3 ohms, when you connect the load, usually the voltage here is going to drop. Actually, you want to keep this one as the same. It doesn't matter you connect the load or you have no load. So we will talk about a voltage regulation later on. That means in general, we expect your output, across the load or with no load is going to be the same. For the battery, 9-volt battery, and you have internal resistance to be 3 ohms, when you short circuit, you're going to have Imax equal to V over R. That means 9 over 3 ohms. This gives you 3 amps. It seems to be like this is give you the maximum current, and I believe that you ever play around with the battery, you just like connect the piece of wire, from negative to the positive of the battery, and actually you make the batteries hot, or you have the heat, because you have like a very very high current, and you have the high power dissipation, because you know that P equal to I squared over R, and you see this is I, this has the power of the 2 or the second here. So I is gonna have more effect to the power than R, because you have that square, the power square here. And this one I show you the symbolic of the current source. Next, talking about our Thevenin equivalent circuit that we often use in electronic circuit. The idea of Thevenin equivalent circuit is that when you have like the actual circuit look like this one, you have the source voltage V in, and you have R1 in series with R2, and you want to connect the load. This one is similar to be like the voltage source, just like a black box, as I mentioned before. Well, Thevenin equivalent circuits say that you can just simply make the complicated circuit with maybe you have more than one voltage source or more than one resistor. It's gonna be easier if you just have like only one voltage source connect to one resistor. I mean, just for the voltage source, and then you can just consider the load later on. Or you can take a look at this one here. You have like VTH, and you have RTH in series, and then you connect the load also in series. This is your RL, this is RTH. It's easy to calculate, so you don't have R1 and R2 anymore, but you simply have only RTH and VTH. So Thevenin equivalent circuit, you can see like you're going to convert the circuit, the actual circuit here, to have VTH in series with RTH, which is different than Norton theorem. Norton theorem is talking about the current source, and you have R in parallel with the current source. But this one is the voltage source. You're going to have R connect in series with the voltage source. Okay, so that's what different. Now you take a look at the circuit here. How do you get VTH, and how do you get RTH when you have R from the actual circuit, R1 and R2? Well, you can say from here VTH equal to V open. What does this mean, V open? V open circuit is mean that you have no load here. Okay, so your VTH is going to be V across R2. So this is how you fire VTH. So it's nothing more than the voltage divider, correct? As I mentioned about it before. So you simply divide input voltage source, which is V in, and then multiply by R2, divide by R1 and R2, because they are in series. So you get VTH. And how do you get RTH? RTH is simply become V open over I short. Okay, we already have V open here, and what about I short? I short is you bring a piece of wire, connect this one to the ground, so you have only R1 left. It's become the current flowing through the system, or flowing through R1. You have no other current, right? So your current I here is simply become, by apply Ohm's law, it's going to be your V in divided by R1. You have this term. And now you want to find RTH. It simply become V open divided by I short. And V open, you already derive, from here. V in multiplied by R2 over R1 plus R2. And then you divide by I short. So simply by multiply R1 over R in, V in cancel out. You have R1 multiplied by R2 and then divide by R1 plus R2. So it's look like it just like become R1 in parallel with R2 from here. This gives you RTH. That's the Thevenin equivalent circuit. Now take a look at example. If I have V in to be 30 volt, R1 equal to R2 is equal to 10k ohms. I want to point you out, with something here. As I mentioned before, you will take a look. When you have no load, you have a certain value of V out. But when you connect the load, your V out drop. So that's the problem of the voltage source that we have to modify. Or let's say we want to keep V out constant. It doesn't mean you have load connected to the circuit or not. I'll show you from example here. Okay, so we start with the circuit with no load. So V out, no load. Just simply you don't have this one, so it's become V out here. It's just apply the voltage divider, so you end up with V in multiplied by R2 over R1 plus R2. Okay, you plug in the number here. It's given V in is 30 volt and R2 is 10k ohms. R1 equal to R2, 10k ohms, 10k ohms. You end up with V out no loads become 15 volt. This is your output with no load. Now if you connect 10k ohms load to the circuit here, you can see that V out 10k ohm load drop, V out drop to be 10 volt. That's a lot. Sometimes you want this one V out still become 15 volt. Okay. Now take a look at the calculation. V out 10k ohm load. It simply you will have R load and R2 in parallel. So you apply voltage divider. You simply divided V in multiplied by R2 in parallel with R load, and then divided by R1 plus R2 in parallel with R load. And you know that this is they have the same resistance, 10k ohms, 10k ohms. When in parallel is dropped to be half of that, so it's become 5k ohms. That's why I have 5k ohms here. And then you divide by R1, it's 10k ohm, and then plus R2 in parallel with RL. So let's give you 10 volt. Dropped out here. This is no load, and this is 10k ohms load. This is not very good. Okay, but we will discuss how to keep the output voltage, the same or constant later on. This is just the basic calculation and give you idea. You can analyze your circuit here. Now Thevenin equivalent circuit. Okay, I have something wrong with my scanner here, so it's difficult to see. Don't know what's wrong. Okay, so our Thevenin equivalent circuit, you take a look at above here. You simply want to get our VTH and RTH as we did before. Let's start with RTH. How do you find RTH? You simply become the open circuit of the circuit. That's mean you have no load here. So you just look for V out. V out is going to be the same, or this is the same as V out of no load. So it's become 15 volt. And what about I short? I short is mean you have a piece of wire connect to the ground here. So your I short is just become V in is 30 volt divided by R1 is 10k. So you're going to have what? 30 divided by 10k is give you 3 milliamp, right? So you have I become 3 milliamp. And you can find RTH. Simply become V open. What is your V open? V open is the same as V out no load, 15. So you divide by I short. This is like 3 milliamp. You get what? 5k ohms, right? This is your. You can get your Thevenin equivalent circuit. So this one is become 3. Sorry. This. Yeah, 5k ohms right there. Now, if you have the load connected to the circuit, as from C, you know that VTH become 15 volt. You want to find V out here, and your RTH, I already showed you, it's 5k ohms. So you use the voltage divider, you're gonna end up with the V out to be 10 volt, at the same as from B, right? From part B, you have the load connected to the circuit. Now take a look at the power dissipated in each resistor. This is the actual circuit here. To find the power, you simply you can play around with I and R, because your tape have R here, so I'm going to use equation P in terms of I and R. What you need to do is you need to find the current flowing through each resistor. Take a look at this one here. R2 and R load in parallel, and they are equal. It's 10k ohms in parallel with 10k ohms, so it's give you 5k ohms. And R1 is 10k ohms. So you add that up, R1 plus R2 in parallel with RL, it's give you 15k ohms. You can find the current flowing through R1. So the current flowing through R1 is V in over R. V in equal to 30 volt, right? What is your R? R is going to be R total here in the circuit, and I have R total to be 15k ohms. So 30 volt divided by 15k ohms, you end up with the current is 2 milliamp. That means 2 milliamp is the current flowing through R1. Now you already know the power dissipation on R1. That's why I have here PR1 equal to I square R. So simply 2 milliamps square multiplied by 10 k ohms. Okay, you can calculate for your number here. What about the power dissipation across R2? Same thing. Since you have our 2 milliamps, flowing through our R1, and at the node, this take the portion of current will flow through R load and R2. Since R2 and R load are equal, R is 10 k ohms, the same, right? So this one split to be 1 milliamp and 1 milliamp. So that's why I have PR2 here. 1 milliamp square multiplied by 10 k ohms, and this is 1 milliamp square multiplied by 10 k ohms. So basically you're losing your power here. You will want all the power, to get as much as power, through the load. You require RTH to be very small, or R1 very small, and we will discuss about it later to get the maximum, power. So let's get back to the circuit here. You start with the actual circuit. You have V in 30 volt, and you have R1 and R2 in series, 10 k ohm and 10 k ohms, and this is your V out port. You're ready to bring the load, or the electronic devices, connect to, this node here. And if you apply a Thevenin equivalent circuit, it's end up here, your V from 30 volt is become 15 volt, which is our VTH. And your R, you have 2R here, you end up with RTH, become 5K. This is the Thevenin circuit. Sometimes we call 5K is the source resistance, or sometimes we call internal resistance, or even Thevenin resistance. Now, what interests you is that you want to find the power transfer across the load. When you have the load here, I want to find the maximum power transfer to the load by using the circuit above. Okay, the circuit. I have V in, I have R1, I have R2, and I have our load connected to the circuit. What are load supposed to be? If I want the power transfer to the load to be maximum power transfer, in this case, I'm going to use calculus to show you that for the circuit, if you have a Thevenin circuit like this one here, you connect your RL, and I want maximum power transfer to the load. The answer is that RL have to be equal to RTH, or in this case 5k ohms. Okay, I can prove that, but let's start with some cases. Okay, case 1. Okay, you can bring that circuit down here. In case you have no load or open circuit, the power you don't have to consider at all. The power transfer to the load is become 0. Why? Because your R load becomes 0. Because P equal to in this case you have no R load. You can put like P equal to I square R. Since your load becomes 0, R becomes 0, so P equal to 0. Case number 2, R load equal infinity, also give you the power transfer to be 0 as well. Why? Well, for I, flowing through the load, is become V over R load, but since your R load become infinity, your current becomes 0. So from P equal to IV, I becomes 0. This gives your power to be 0. Now consider maximum power transferred to the load. As I told you that RL is going to be equal to 5K or equal to RTH. Okay, let's start with this one here. This is your V out and this is your R load. And V out, simply, you pick up this Thevenin circuit. V out is become a voltage divider. You divide VTH and multiply by RL, and then divide by RL plus RTH. Power to the load is become V squared over R. You already have V here, so you simply square this term. So I have VTH squared multiplied by RL over RTH plus RL squared, and then divide by R load. So that's why I have R load here. And then from the plot, from P and R relation or PR curve, on the x-axis is the RL and the y-axis is the P load. If you plot, you're going to have the the plot like this one, and you use the concept that the highest point or the maximum point, your slope of the plot has to be 0 to be able to give you the maximum power to the load. So what you need to do, you need to differentiate power to the load with respect to RL, and then make it equal to 0, and you solve equation to find RL, and finally you will see that your RL is going to be equal to RTH. In that case, give you the maximum power transferred to the load. This is basic calculus. Okay, there's something missing here because some a problem with scanner. Alright, so you differentiate here with respect to RL. You keep VTH square, and you differentiate this term. Let's see here. You differentiate just power to the load with respect to RL. The first term you differentiate is become actually this one I should have this is become, I cancel this one out. Alright, and then you have RL over RTH plus RL to the power of 2. First you differentiate this one, so you have this one left. Actually I should have this one here square, and minus, keep this one RL the same, and you differentiate this one, so it's become negative 2, and then RTH over RL. This is to the power of 3. Okay, you can work this one out, and then you can prove that RTH equal to RL. Okay, in this case we call, when you want the constant output voltage, in this case when you connect load resistance to the load N here, and you know that the maximum power transferred to the load is going to be maximum if your load here is equal to RTH, and that's we call match on the circuit. That's what you expect. You don't want to lose your power here, so you get the maximum power transfer to the load. Next, since we're talking about a constant output voltage, that's why we bring up our Zener diode here. Well, the way you connect your Zener diode, and that will give you the constant output voltage. First, we take a look at the sorry. You take a look at the IV curve for resistance. You know, or V equal to IR, and you have a linear relation between I and R. So that's why you got a straight line here, and the slope of the plot will give you a resistance. So your I over V, V over I. In this case, let's start again. You want to find from Ohm's law, V equal to IR. You want to find delta I over delta V. So I over V actually is become 1 over R. When R small, you will have a large slope. Okay. And when you have R big, you're gonna have a small slope. So that's why this is R2. R2 is greater than R1 when you compare two lines. This is line of R1 and this is line of R2. So this is R2, you have less slope, you know, compared to the slope of R1, because R1 is less than R2. Okay. But IV characteristic of the Zener diode is not going to be a linear, or we call it is not linear. It has the IV characteristic like this one here. When you have V0, you have the current flowing through the circuit or through the diode here. At some point, when you are supplying the voltage across the Zener diode, you're going to the diode still start conducting. So you have the curve, you know, increasing here. You have increasing current. So this is what we call the forward, you know, bias. You have the you apply the voltage. When you apply the negative voltage, you're going to have the breakdown. That's I will discuss more detail about the diode's characteristic later on. And this one for the ideal diode, supposed to be like this. When you supply the negative voltage to the diode, at some point it's going to break down. Okay, so diode is just like is one of electronic component that work as on-off switch, but only allow the current flowing into only one direction. And it also have you need to supply, you know, positive on this one and negative to this one to be able to conduct the current, and that's what we call the forward bias. Okay, so don't worry about that. I will discuss about the diode characteristic later on. But in this case, we are interested in how Zener diode connect to the circuit, how it's keep the output voltage constant. There's a lot more to talk about diodes. Okay, just for example, if I have R forward, you take a look at this one. What the difference between resistance of a resistor and the resistance of the Zener diode is that the resistance of a resistor always constant. It's never changed with the supply voltage. But if you take a look at the Zener diode IV curve, you know that the resistance of the diode corresponds to or associated with the slope of the plot, and you know that at each point you don't have the same slope, or it means that you don't have the same resistance of the diode. It changes with the input voltage that's applied to the Zener diode. That's why they have the I wrote out this one R forward at 10 milliamp only at this certain current level. At 5 volt it's become 10 ohms. If you take a look at this one here, so 10% change in applied current result in delta V equal to R delta I. This is like follow Ohm's law, V equal to IR. So at I around 10 milliamps, you have your R become 10 ohms. That's why I put 10 ohms here. And if you have 10% change in applied current, you can find percent change of the output voltage also. So 10% change give you a 0.1. You multiply 0.1 to 10 and to 10 milliamp. That's give you delta V equal to 10 millivolt. You can see that it doesn't change a lot. It's saying only 10 millivolt. Or you can find voltage declaration. Simply divide delta V by V. You have the change of the output voltage 10 millivolt when you supply the voltage to the diode 5 volt. So you end up with 0.002 or only 0.2%. So this gives you the good voltage regulating ability from the Zener diode. You try to avoid large percent change of the output voltage, as I discussed before. When you use resistor, you have voltage drop, output voltage drop when you connect the load to the circuit. But here, when you use the Zener diode, the percent change of the output voltage is very small. This one is 10 milliamp at 5 volt. That's why you divide 10 millivolt by 5 volt. Or from the circuit above, you can calculate for the current flowing through the Zener diode. This is your V out. Okay. Sorry. You can calculate the current flowing to R here. This is your V out. So your current simply become V in minus V out, and then divide by R. Or you put like delta I is going to be delta V in minus delta V out over R. And this is your V out across the Zener diode. Apply the Ohm's law, V equal to IR. So it's become R forward multiplied by delta I, because we already have delta V here. Now what is your delta I? This is your delta I. So you are substitute this one into delta I. So you have R forward multiplied delta V in minus delta V out over R. Okay. And then you rearrange this term just to have V out. You're going to end up with R forward over R plus R forward multiplied by delta V in. It's just like voltage divider, correct? This is your V in, and this is you have R forward here, just like R. We did that before. And then you have R in series with the source voltage and in series with the Zener diode. So you divide by R plus R forward. Now take a look at the example of the design. If you want to design 5.1 volt power supply, or you want V out to be 5.1 volt, and you have input voltage in the range of 15 volt to 20 volt, and if I use Zener Diode 1N473, which has spec of 5.1 volt, 1 watt, and also come with R forward to be 7.0 ohms at 50 milliamps. Okay, design the circuit. That means you need to find R here, because you already know the Zener diode, and you know the range of V in, and you expect V out here to be 5.1 volt. How will you decide that? Okay, now let's take a look at the maximum voltage here. You want to find R? Let's pick up here by using the V in maximum 20 volt. So you are here from Ohm's law. R simply become V in minus V out over I. So your V in maximum is 20 volt, and your V out, you want V out to be output to be 5.1 volt, and then you have spec here the current at 50 milliamps. So you divide by 50 milliamps, you end up with R to be 300 ohms. Okay, next, you also find minimum current by using the minimum input voltage 15. So 15 minus 5.1 divided by 300 ohms that you already designed, from this here. You get the minimum current to be 33 milliamps. The reason we do this because we want to find delta I. So you have different delta I when you have the input voltage in the range of 15 to 20 volt. Delta I's become 17 milliamps. Or you can find delta V as we did right before. Delta V out become R forward multiplied by delta I. And R forward is given here from the data sheet. At 50 milliamps, you have R forward to be 7.0 ohms. So you simply multiply 7.0 ohms multiplied by delta I, which is 17 milliamps. You get delta V becomes 0.12 volt. This is your delta V, or how much your output voltage gonna change due to delta I, change. So let's give you just the basic technique to design, your circuit. This is the just for to get a good voltage regulating ability by using a Zener diode. Okay, next, since the last time when we talking about a voltage divider here, okay, from the previous circuit, this is your V out, this is R1, this is R2, and this is V in. Now you take a look at that tunneling diode. The IV characteristic curve of tunnel diodes look like this one. From point A to point B, this gives you negative resistance because the slope become negative, right? Beyond this point, slope are all positive. This negative slope. So when you compare the circuit, this is the way you connect the tunnel diode. You take a look at this one, and you consider only the AC signal only. You use the voltage divider, your V out, simply become your V out. This point simply become divide V signal multiplied by R over R plus RT. Which is RT is the resistance of the tunnel diode, and it's obviously that when RT become negative in the range from A to B, this one gets smaller than R because R minus something. So V out become larger than V signal. That means you amplify your input signal. Okay. Next, we talk about our signal in electronic circuit. Previously, we talked about signals. It's the DC signal, and then talking about a voltage, you're talking about a current. Seem to be like constant, not depend on time. Now we will talk about a signal that also change with time, and that's going to get involved in capacitor and inductor. That's why I talked to you about we will get into deeper in electronic devices. So we start by looking at different type of electronic signals. For sinusoidal signals, you can write or you can represent your voltage signal by equations. V equal to A sine 2 pi f t, where A is the amplitude of your voltage signal. Or A you can put like psi multiplied by psi omega t, where omega is the angular velocity, become radian per second, and this all represent amplitude and frequency. You take a look at the plot between the voltage and the time. This is your amplitude, the maximum voltage, and this is your period. That's equal to 1 over f. You can draw the plot like this one here. And sometimes you also have the phase, it's come to play in the voltage equation, also. They're talking about a sinusoidal signal in electronic circuit because it's dealing with linear circuit. What does this mean, linear circuit? When you have two different circuits here, you have different input. This is V input 1 to get V output 1, and circuit number 2 you have V input 2 and then you have V out 2. What about if you have input to be V in 1 plus V in 2 and pass into one circuit? And if you pass to one circuit, you have V out, and your V out of V in 1 plus V in 2 can be written as V out 1 plus V out 2. You can say that your circuit is linear. Okay, this is just for your information. And sometimes we write, when you use the sinusoidal signal, you can find the frequency response. What does it mean, the frequency response? For the axis it's become frequency, and the y-axis become the gain. What does it mean, the gain? The gain is like the ratio of V out over V in. Okay, and when we will get into more details about it later on. And this one I write down is if you have a microwave waveguide, you want to send signal, because you're talking about a frequency here. If you want to send signal with a very high frequency, for this example, like it's greater than 2 gigahertz, you cannot use just electric wire or the basic circuit with the wire connect to electronic components RC. Cannot do that. You have to use microwave. You have to use the waveguide or strip lines to be able to send that kind of signal, very high frequency signal. Okay, they are also can define signal amplitude in decibel. You're probably familiar with the unit of decibel. First, we take a look at somebody confused about VRMS and V peak to peak. When we're talking about a peak to peak, you find, it's going to be double of the amplitude of the voltage. But in the real life, usually we're talking about VRMS. Just like when you use the voltage source 220 volt, for electric appliance in our house, we usually talking about the voltage in VRMS. But actually, if you want to compare to peak to peak, you need to multiply 220 volt with square root 2, and it gives you 311 volt peak to peak. So keep in mind that what we're talking about, any calculation or any kind of voltage that we talk, of everyday life, we're talking about VRMS. Now go to decibel. Decibel is equal to 20 log 10 of V out over V in. This one actually is the gain. For example, if you have V out become the double of V in, so you simply have log 2 base 10, and that gives you 0.3010. Or you can even apply dB for the power 2. For acoustic, 0 dB SPL, talking about the RMS pressure, equal to 0.0002 microbar, which one bar is the pressure unit, equal to 10 to the 6 dynes per centimeter square, or it's about 1 atm. When you're talking about 3 dB, you want to find V out over V in, or you want to find the gain. How many times V out of V in? So you make it equal to 3 dB, and your V out over V in have to be your divide 3 by 20, and you make V out over in become 10 to the 3 over 20. Or you take a look at this one, V out over V in is become 3 over 20, and then you move 3 3 over 20, so you have 3, and you have log 10. That's 10, right? And this has become 1, so that's why you end up with 3 dB. Other signal, you're probably familiar with this already. Ramp waveform, ramp width limit, sawtooth, triangle, noises. Typically we talk about the band limited white Gaussian noise. It means the signal with equal power per hertz. Okay, so it's not so difficult for you to understand. Equal power per hertz, and have the distribution of, like the plot, just like the Gaussian distribution. That's why they call it as the Gaussian noise. And you also have step, you have spike. We will get in two more details about all of this later on. So this is also we will talk about the digital logic. So my objective to give you the basic electronic is to start with something that will lead you to understand more about electronic. Thus I will get into deeper and deeper and more complicated of electronics. Later on we will talk about a transistor, we'll talk about op amps, we'll talk about almost many things of electronics. Hopefully you get some idea that will lead you to understand about electronic world. So I will present more in the next YouTube. So this one is just to get start or refresh. I believe that most of you understand part of this already. So let's, for this YouTube, let's stop just right here.